In this video lab report, I will be discussing and analyzing the motion of a tennis ball falling. Using Newton's second law, we will decide which forces must be considered to predict the tennis ball's motion with a computer model. The first thing we'll do is track the real-world data of a tennis ball falling. Then we'll make a computer model, assuming that the only force on the tennis ball is gravity. Then we'll make a second computer model, assuming that the forces acting on the tennis ball are gravity and drag force. You'll see that the gravity model will overpredict the distance that the ball falls, while the gravity and drag model will be a much better approximation to our real-world data. These results tell us that gravity and drag force must be taken into account to make a good model of a falling object's motion. Let's get started. Here you can see the real-world motion of a tennis ball falling analyzed in Tracker. The origin was set at the initial position, and the ball dropped from rest, giving the tennis ball an initial position and initial velocity of 0. The motion was calibrated with this ruler, and the axis was tilt to compensate for the tilt of the camera. The position of the tennis ball was marked as it fell, and you can see the data on the right side of the screen. Here's a graph of the y position of the ball versus time. The graph is a downward-facing parabola, which indicates that the ball was accelerating in the negative y direction as it fell to the ground. Now let's see if we can predict this motion with computer models. The equations we need are Newton's second law to solve for final velocity and the definition of velocity, which we rewrite here to solve for final position. Recall that we determined the initial velocity and initial position to be 0, and also that we know the mass of our tennis ball. Therefore, if we pick a reasonable net force, we can solve for the final velocity, and then use this value to solve for the final position during some time interval, delta t. The computer will use these two equations to try and predict the motion of our falling tennis ball through iteration, or solving the equations repeatedly with some small delta t, and it will continue plotting data points until we tell it to stop at 0.467 seconds, because this is the time of the last data point that we measured. Let's input all of the information we just discussed into our VPython code. Here's the initial conditions and our small delta t, more initial conditions and our direction, and finally the while loop where our iteration happens. Here's our final time, the net force, which we're calling gravity, or negative mass times the gravitational constant, and here's the two equations we want the computer to use, Newton's second law and our rewritten definition of velocity. This is the program's prediction of the tennis ball's motion. The data is plotted here, and it's a pretty good fit. But let's see if we can come up with a model that does a better job of predicting the motion towards the end of the time interval. Let's consider the drag force acting on the tennis ball, which we define to be some constant b times the velocity squared. Now our net force is equal to the force of gravity in the negative y direction plus the drag force in the positive y direction. We add this equation for drag force and change the equation for our F net in the code here. Constant b depends on the airflow around the tennis ball, which is caused by its shape and size. To find a good approximation of b, we ran the model using different constants until the final position matched the final position we measured in our tracker analysis, 0.969 meters. The constant b in this case was 0.018. Here's what it looks like when we run our new model. You can see the drag force here. Here's our comparison of our real-world data, the blue dots, with our two models of the tennis ball falling. A model that contains only gravity overpredicts how far the ball falls. However, the model that considers gravity and drag force, this orange line here, makes a much better prediction. It's important to note that we ensured the last points would match up when we used our final position to find the constant b. However, you can see that the graph is a good fit in all of the other points as well. Some places where the points don't match perfectly, like right here, are most likely caused by errors from not clicking perfectly in the center of the tennis ball. In conclusion, we can use Newton's second law and the definition of velocity to create computer models that predict the motion of falling objects, and these models will be a better fit if we account for both the forces of gravity and drag. Some additional notes. Terminal velocity is the velocity of a falling object when the net force equals 0. In our gravity model, this makes no sense. However, in our gravity and drag force model, if you can set the force of drag equal to the force of gravity, and actually calculate the terminal velocity. Therefore, only the gravity and drag model allows you to predict terminal velocity. But what if the initial velocity of our tennis ball wasn't 0? You can see that both the dropped tennis ball and thrown tennis ball eventually reach the same constant slope, or constant terminal velocity. It turns out that no matter what the initial velocity of the tennis ball is, it will speed up or slow down until it reaches constant terminal velocity.